Hi. So we have this question before us. It is a binomial sum, and we want to find out the value of k here. What is this looking like? It is NCR plus 5 times NCR plus 1 plus 10 times NCR plus 2, and so on, this numerator, by a denominator which looks very similar, but in terms of 4, 6, 4, 1. And this is equal to n plus k by r plus k. And we have to find the value of k, right? So let's try to understand this pattern here. Let's work on the numerator for the moment. So think of the numerator. It is 1 into NCR plus 5 into NCR plus 1, 10 into NCR plus 2, and so on, right? Now, you can easily spot that 1, 5, 10, 10, 5, 1. These are just 5C0, 5C1, 5C2, 5C3, 5C4, and 5C5, right? So we have a nice series where there are products of two binomial coefficients, 5C0 and NCR, 5C1 and NCR plus 1, 5C2 and NCR plus 2, and so on, right? Okay, so how do we simplify this? So right now, notice that the subscripts here, 0 plus r and 1 plus r plus 1, do not have the same value. Every subscript is increasing, right? Here the sum is r plus 1 plus 1, so r plus 2, and here it was only r, and here it is r plus 4, and here it is r plus 6, right? But if we do a slight change here and convert 5C0 to 5C5, which is equal, because we have the property that NCR is equal to NCN minus R. Using that property, we can convert 5C0 to 5C5, 5C1 to 5C4, 5C2 to 5C3, and so on. So now you notice that the subscripts are adding up to the same value, right? 5 plus R, 4 plus R plus 1 is 5 plus R, 3 plus R plus 2, this should be, I have made a mistake here. 3 plus R plus 2 will also be 5 plus R. And 2 plus R plus 3 is 5 plus R, 1 plus R plus 4 is 5 plus R. So that is a huge step for us, because that gives us a hint that this series could come as the coefficient of x to the power 5 plus r, x to the power 5 plus r in some series, because we know binomial theorem concepts that I will show you on the next page. So if you have 1 plus x to the power n, coefficient of x power r is NCR, right? So now here, because we had 5C5 into NCR plus 5C4 into NCR plus 1, and so on, and more terms like this, let's think of coefficient of x to the power r plus 5 in the product of the in the series 1 plus x to the power 5 multiplied by 1 plus x to the power n, right? So we can easily get this, because this is actually 1 plus x square, 1 plus x square with 1 plus 5C1x plus 5C2x square, and so on, till 5C5x power 5. And this is just 1 plus NC1x plus NC2x square, and so on, till say NCR x power r, and so on, higher powers, right? Now, if I am looking for coefficient of r plus 5, how will I get r plus 5 after multiplying? I can start with the constant coefficient term here. So I have to select 1 here. So that will be 5C0. And I have to select the term here that has r plus 5 power, right? X power r plus 5. So that will be NCR plus 5, right? Then I can select the power 1 here. And I'll have to select r plus 4 power here, right? So it will be 5C1 into NCR plus 4. And finally, similarly, 5C2 into NCR plus 3. And finally, you'll get 5C5 should be multiplied by NCR, right? 5C5 into NCR. So that just gives us the series in the numerator that we were looking for. And that is basically now coefficient of r plus 5 in this expansion, which can be written as 1 plus x to the power n plus 5. And therefore, that is very trivial. It is just n plus 5 c r plus 5. So my numerator is simply becoming n plus 5 c r plus 5. If we follow the same exact process in the denominator, we will get the answer for the denominator as well. So let's look at the denominator. What was the denominator for us? So it was NCR plus 4 times NCR plus 1 plus 6 times NCR plus 2 plus 4 times NCR plus 3 plus NCR plus 4. And I noticed that this is 4C0 NCR plus 4C1 NCR plus 1 and so on. Exact same steps, replace it with 4C4 NCR and this becomes 4C3 NCR plus 3 R plus 1, and the last term becomes basically 4C0 into NCR plus 4. So this is basically simply exactly same like the numerator. It is coefficient of x power r plus 4 in the expansion of 1 plus x to the power 4 and 1 plus x to the power n. So that is simply 1 plus x to the power n plus 4. So that is n plus 4 c r plus 4, right? And for the numerator, we got n plus 5 cr plus 5, right? N plus 5 cr plus 5. So the answer for us will be basically n plus 5 cr plus 5 divided by n plus 4 cr plus 4, which on simplifying becomes n plus 5 factorial by n plus 5 minus r minus 5. So n minus r factorial r plus 5 factorial divided by n plus 4 factorial, and on top goes n minus r factorial and r plus 4 factorial, right? So here n minus r factorial will get cancelled, r plus 4 will get cancelled here, and it becomes simply r plus 5 without the factorial sign, and this n plus 4 factorial gets cancelled and it becomes n plus 5. So you're getting n plus 5 by r plus 5. And the left hand side was written like n plus k by r plus k, and therefore k must be 5. So what was the idea behind this question? The idea was to recognize that we have a property that NCR is equal to NCn minus r, and once you replace the coefficients, the subscripts of the two binomial coefficient will add up to a constant number. And if subscripts add up to the same number, then it must be coefficient of some x power something in a binomial series. You just have to figure out the series. So that will come if you write down the terms carefully and think about it, and you can look through the solution again to get a hang of it. Hope this answers your question. I have another question now. This is question number 2, which I will also answer for you. Let's see. The question is the value of the sum. The value of the sum from k goes from 1 to infinity. K goes from 1 to infinity. And there is a double summation here. This is n goes from 1 to infinity. K goes from 1 to infinity, n goes from 1 to infinity, and it is k by 2 power n plus k, right? K by 2 power n plus k. And we have to find the value of this sum, right? So let's try this. It is actually fairly straightforward. So understand that when you are doing a summation on n, then the k part remains constant, right? So k part doesn't change if I do a summation on n. So what I can write this as k by 2 power n into 2 power k, and this is being summed over n, right? This inside part, right? So now here, since it is a summation over n, k and 2 power k doesn't change. For each term, it will remain the same. So I can take that out of the summation. So I can write the overall thing is k is equal to 1 to infinity, k by 2 power k. And inside part is summation of n is equal to 1 to infinity, 1 by 2 power n, right? So this is my summation after simplifying and taking out the k part outside, right? Now this is a simple infinite GP. This is an infinite GP. So notice what are the terms of this infinite GP. The first term will be 1 by 2, then second term is 1 by 2 square, and so on, right? These are the terms of this GP. So sum of an infinite GP is a by 1 minus r. A is the first term. So first term is 1 by 2. Common ratio is half. So 1 minus half. So this is just 1. So this infinite GP is summing up to just 1. So our summation basically becomes k is equal to 1 to infinity, k by 2 power k, right? Let's do that on the next screen. It is just k by 2 power k, from k goes from 1 to infinity. Okay, great. So this series, if you write the first few terms, it will become an AGP, because you will notice that the K values are increasing, and clearly there is an AP 1, 2, 3 and a GP 1 by 2, 1 by 2 square, 1 by 2 cube, and so on, and which have been combined. So we know how to sum an AGP. The sum of an AGP should be done like this. Let's write down the terms here first. And so on. This is an infinite sum. And let's multiply. What is the common ratio of this GP here? The common ratio of the GP is half. So let's multiply by the common ratio of the GP on both sides. So half S should be equal to 1 by 2 square. And I will write the series by shifting it to the right by one step. So I'll write 1 by 2 square here. And then I'll write 2 by 2 cube. I'm multiplying each term by half and writing it by shifting it a little bit to the side, right? So it will be 3 by 2 power 4 and so on, right? Now notice that if we subtract these two series, right, this side becomes S by 2 and this keeps coming down as it is. And what happens to this? 2 by 2 square minus 1 by 2 square. So 1 by 2 square plus this becomes 1 by 2 cube plus 1 by 2 power 4 and so on. And that is an infinite summation, right? This is subtract, 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 right? Now, this infinite GP is also very easy to evaluate. The first term is basically 1 by 2 square or 1 by 4, and the common ratio is 1 by 2, right? Common ratio is 1 by 2 between the terms. So 1 by 4 by 1 by 2. So 1 by 4 by 1 by 2, the answer of this GP is half, right? So this GP sums up to half. So it is half plus half, which is equal to 1. So therefore, I have S by 2 is coming as equal to 1, and therefore S is equal to 2, which is our answer for this problem. So this was a fairly straightforward thing. The key idea was to be able to separate the K part and the N part, and do the K part first or N part first, and then get to the K part. You will be using the sum of an infinite GP in both cases. You will also be using the technique of how to find the sum of an infinite AGP, right? And this is the technique. You write the series, the AGP series, and then multiply by common ratio and transpose the terms to the right by one step, and then subtract. And that it boils down to a GP summation in the end. So hope that answers your question, and I'll see you next time.